right, here we are. Justin Miller here at Oxnard College. I'm gonna go do some physics now. So the topic for this session is going to be velocity-dependent resistive forces. Ultimately, as an object moves through a substance, being something like air or a fluid, it needs to push that substance out of the way to occupy its space. And that produces a resistive force acting on that particular object. And in general, the faster an object is moving, the greater the resistive force, because the more material it has to move out of the way per unit time. It's coming into contact with material more and more, and that produces a greater and greater amount of force. So we're going to look at a simple sort of model where the velocity-dependent force is directly proportional to the velocity of the object. This particular model is best used for objects moving through fluids where the buoyant force is non-existent, we'll just say, doesn't impact the system, or objects moving through air at slow rates. Once objects move at reasonably large rates through air, another model takes over. We'll discuss that at a later point in time. But ultimately, this is what we've got. We've got ourselves that can take an object, and I can let go of it, and this kind of floats down. I can take that same object, and I can change its spatial orientation and drop it, and it does something completely different. It doesn't just float down, it still moves downward with some forces acting on it, but they're not as much as they were in the previous case where it was laid flat. I can also take that object that is flat and just drop it like this. And, whew, you don't see it go all the way to the ground, but kind of zip down a little bit different. So there's something about the spatial orientation of the object and the orientation of it itself with respect to the direction that it's moving that impact how it has to interact with the substance in which it's immersed. So what we have here is a system which we're going to go ahead and model out and see what we can figure out about the time characteristics of the object's change in velocity. So we're going to look at velocity-dependent resistive forces. And we're going to take that resistive force, call it R hat, and say that it is equal to negative B, V hat. So R hat is the resistive force vector. V hat is the object's velocity vector. And B is the constant of proportionality. Which depends on the object and the substance through which the object moves. The negative sign here, that tells us that the resistive force is in the opposite direction of the object's motion. That's it. This is what we've got going on. So we're going to start off by looking at a particular case in which an object is initially at rest and released into some substance at t equals 0. And we're going to assume that the only forces that will be acting on this particular object are Number one, the gravitational force, we're locally close to Earth. And number two, the resistive force. As the object's speed increases, that resistive force will then increase. So, let's go ahead and take a little model here. We got ourselves some sort of fluid. We can take ourselves an object that has some mass m, and we can say that it's initially at rest. So we've got an initial velocity of 0, that's great, and we're going to go ahead and release this object into this fluid. We note that there will be this force due to gravity, and this resistive force will pop up once the object starts moving. So once the object begins to move, the resistive force comes into play. So what we want to do is say, well, what's the net force acting on this object? And can we utilize some of Newton's laws in order to figure out what the actual evolutionary behavior of this object is? So let's just do that. We've got this. We've got the net force acting on the object will be equal to the sum of all forces acting, which in our particular case is going to be F sub g hat plus r hat. From this, we can go ahead and say, well, we know what F sub g hat is, that's mg hat. And we know what r hat is, that's negative bv hat. Let's just go ahead and throw that stuff in there. So we've got net force acting will be mg hat minus bv hat. What do we know about this? Well, the net force produces the acceleration of the mass. And thus, we must have ma hat is equal to mg hat minus b v hat. Solving this for the acceleration, we can go ahead and say that the acceleration vector is going to be equal to g hat minus b over m v hat. So there's the acceleration as a function of velocity. What do we know? The velocity is changing, then the acceleration is changing. This is not a case of constant acceleration. The acceleration is not constant, v hat's changing. As this object goes from a zero velocity to a non-zero velocity, we've got a changing velocity, we've got a changing acceleration. So we can't utilize equations of motion for constant acceleration because they don't apply to this case. What we can do is still go back and look at the explicit definition of acceleration itself. So let us do that. We've got acceleration by definition is the rate at which velocity changes with respect to time. And a hat is defined by dv hat dt. There we go. So let's just go ahead and stick this in. We've got then that dv hat by dt is equal to g hat minus b over m v hat. This is a nice little expression here. It says the rate that velocity changes with respect to time is equal to some constant minus some other constant, which is just the ratio of b over m, multiplied by the velocity itself. This is a differential equation. If you've never taken differential equations before, that's okay. Ultimately, there is a solution for this. Some function, v, that is a function of time that we stick into this expression and it solves it out. It gives us a constant and gives us that same function back. So, what we need to do is not so much focus on solving this out, but ultimately having a solution for it. So this is something that's actually directly integrable. Not going to do it here, but we could start getting all the v's on one side, all the constants on the other side, throw dt over here, have a dv over v sort of thing over here, and we can come up with this particular solution. A solution for this expression is v of t is equal to v sub t times 1 minus e to the negative bt over m. What we got to do is understand what all this stuff is. So this is the function that describes the velocity with respect to time. This v sub t here, this is known as the object's terminal velocity. V sub t is the object's terminal velocity. It is ultimately the maximum speed that this object will reach. See if we can figure out what that v sub t actually is. Is it just some number, or does it have something to do with other things that are at play here? So the object's final speed, or the object's terminal speed, will be reached when a hat is equal to 0. No more acceleration. If there's no more acceleration, we've got the velocity is constant, and that's what we define as the terminal speed of the object. So if we go back over to our function here that we began with, this, we can actually figure out what v sub t is. So again, referencing this, we have that a hat is equal to g hat minus b over m v hat. And we can say that a hat is equal to 0, is equal to g minus b over m v sub t. So we kind of get rid of the little vector signs, don't really need them. We're really just identifying the speed of the object when the acceleration is 0 and saying that that is indeed the terminal speed, v sub t. So we can solve that out for v sub t, and what are we going to get out of that? Well, it looks like we're going to get mg over b. V sub t is equal to mg divided by b. So the terminal speed of the object itself depends on the mass of the object, obviously the gravitational acceleration, and then this constant proportionality that's explicitly determined by the spatial composition of the object and material properties of the fluid through which the object is traveling through, primarily. There we go. This is our terminal speed. So at that, this v sub t is really just mg over b. And what else do we find? Well, we've got this part of the function here. This gives us the variation with respect to time in terms of the maximum speed that can be accomplished. So let's look at this function a little bit more and see exactly what we've got going on in terms of some endpoints. Make sure that our boundary conditions are met. That is, we know what should be happening at t equals 0, and we know what should be happening sometime thereafter. At t equals 0, we have v of t equals 0 is equal to v sub t times 1 minus e to the negative bt over m. Well, that's going to be e to the 0. At t equals 0, we just throw in the 0 up there. We've got this. What's 1 minus e to the 0? That's So it's going to be equal to 0 because e to the 0 is equal to 1. So this is equal to 0. That's what we want. We had said that this object is initially at rest. So that checks out. Great. We've also got, after some amount of time, maybe a whole bunch of time, but that's relative, the object should be at its terminal speed, right? So we can look at t is equal to, hey, let's say infinity. Well, we have that v of t is equal to infinity is equal to v sub t times 1 minus e to the, well, we just put in negative infinity. What's e to the negative infinity? 0. So what do we get with this? This ends up being v sub t. Well, that's the endpoints. The start at 0, the end at the terminal speed. That's what we want. So this checks too. So what we want to do now is go ahead and investigate what's going on between. That's this function here. It tells us what the evolutionary behavior of the object's velocity is with respect to time. So let us proceed. Let's define what's known as a time constant. Time constant tau, we're going to say, is equal to v divided by n. M divided by b, excuse me. So we got ourselves tau m divided by b, and the reason that we go ahead and define this is now we can write that v of t is equal to v sub t times 1 minus e to the negative t over tau. So that bt over m now just becomes t over tau, with tau being equal to m divided by